We have some practice here. You have this Lewis structure of SO4 2-, but you have to check the formal charges. So for sulfur, you have to do 6 minus 1, 2, 3, 4, which is plus 2. And you know that plus 2 formal charge is not common, and atoms will not favor the formal charges as big as 2. And for this oxygen, 6 minus 1, 2, 3, 4, 5, 6, 7, -1. And all these oxygen molecules will have a formal charge of -1 as well. And you can easily see that this is not a favorable Lewis structure. So you have to find the Lewis structure that the molecule will probably have. And the way to do that is just making double bonds on 2 of these oxygens. So you draw the atoms here, and then you make a single bond, and then you have to make the double bond for 2 of these oxygens. And then you put the leftover electrons and fill the octet. Then you check the formal charge, and then it will be 6 minus 6, 0 for sulfur, and 6 minus 7, -1 for this oxygen. And you see that compared to this Lewis structure, atoms on this Lewis structure have formal charges more closer to 0. So you see that this is the most probable Lewis structure that the molecule will have. For the second example, you have to find the most probable Lewis structure for NCO-, and you can do that simply by checking the formal charges. Nitrogen has a valence electron of 5, minus 1, 2, 3, 4, 5, 6, 7, -2, which is not good. Carbon, 4 minus 4, 0, and for oxygen, 6 minus 5, which will be plus 1. And you see the Lewis structure of B, 5 minus 1, 2, 3, 4, 5, 6, -1. And carbon, 4 minus 4, 0. And oxygen, 6 minus 6, 0. And for this nitrogen, 5 minus 5, 0. And 4 minus 4, 0. And then 6 minus 7, -1. And you can see that this is not a good choice. So you're between B or C. And you see that for B, -1, the negative charge resides on the nitrogen. But for C, negative charge resides on the oxygen atom. And we just learned from the rules that the negative charges should reside on the most electronegative atom. And in this case, oxygen is more electronegative than the nitrogen. So negative charges should reside on the oxygen, which will make C the most probable Lewis structure. Next is the effective number of bonds. And this is especially useful when you are looking at resonance structures to know approximately what number of bonds the atoms will have. And you calculate them by dividing the number of bonds by the number of atoms bonded. So for nitrogen in here, it has 4 bonds and 3 atoms are bonded to it. So you divide 4 by 3 and you get 1.33 bonds. And for NO2, you do 3 divided by 2, which is 1.5 bonds. And to figure out the bond energy, you have to know effective number of bonds. Shorter the bond, the greater the bond energy. So this means that in order to compare the bond energy between 2 molecules, you will have to calculate the effective number of bonds, and then you will be able to know which molecule will have a higher bond energy. Because if the bond is shorter, the bond energy will be greater. The last topic for today is hybridization. And you have to count the number of charge clouds first to know the hybridization. So bonds, lone pairs, or double bonds, triple bonds, all count as one charge cloud. So sp hybridization is just 2 charge clouds. So for example, BeCl2 beryllium is bonded to 2 chlorine atoms. sp2 hybridization is 3 charge clouds, but you can simply think of sp is just 1 s and 1 p, so 2. You'll have 2 charge clouds. For sp2, you have 1 s and 2 p's, so you have 3 charge clouds. And for sp3, you have 1 s and 3 p's, so it will be 4 charge clouds. So you have to make sure you are not confused with this exponent of p, but you have to add one more to know the charge clouds. For sp3 hybridization, you have the example of PCl3, and you count the lone pairs as 1 charge cloud. So P has 4 charge clouds, and it has a sp3 hybridization. You have sigma and pi bond, and sigma bond is the strongest type of covalent bond, and pi bond is the covalent bond formed by lateral overlapping of orbitals. You do not have to know the specific descriptions, but you have to know how to count them in the molecules. So single bonds, all single bonds consist of 1 sigma bond, and double bonds consist of 1 sigma bond and 1 pi bond, and triple bond consists of 1 sigma bond and 2 pi bonds. So for C2H4, you will have 1, 2, 3, 4, 5 sigma bonds and 1 pi bond, because you have a double bond here, and double bond consists of 1 sigma and 1 pi bond. And for C2H2, you'll have 1, 2, 3 sigma bonds and 2 pi bonds here for the triple bond. And then here, you'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sigma bonds, and then 1, 2, 3 pi bonds. And a quick review for hybridization. For the central atom C, it will have sp2 hybridization because it has 3 charge clouds. As I just said, you do 1s, 2p, 3 charge clouds for sp2. You see that central atom C has 1, 2, 3 charge clouds. For C2H2, the C atom has 2 charge clouds. It doesn't matter what type of bond it is. Even if it's triple bond, it counts as 1 charge cloud. So 2 charge clouds, sp hybridization. And for this molecule, for this C, it has 4 charge clouds. So it will be sp3 hybridization. And this is the end of the video, and thank you for watching.